Hello everyone, I'm Juntao Wang. This is a joint work with Yang Liu and Yilin Chen. Our work, Surrogate Scoring Rules, is about a mechanism that enables us to elicit probabilistic predictions, even when the ground truth is not available. Let's start our motivation with the replication crisis in psychology. Recent research has found that around only half of psychology studies can be replicated. A single replication test will spend around $10,000 and is also very time consuming. So is there a better way to identify which studies can be replicated? An answer is to use the crowdsourcing. In a recent project, hundreds of researchers and students are recruited to bet on the replicability of 21 studies. It turns out that they correctly predict the replication outcome of 18 out of 21 studies. So this is a great success. But notice, in this project, these 21 studies have been put into real tests such that the principal can make incentivized payments to these bettors. Following this idea, the SCORE program has been launched to let knowledgeable crowds predict on 3,000 studies. They gave participants the information about a paper and asked the question, how likely can study be replicated? Then the participants report a probability. The issue here is that the program cannot put all the studies into replication tests because of the expense and time. Only 10% of studies will be tested. The rest 90% studies won't have the test ground truth. This causes the research problem. How can we incentivize high-quality prediction when the ground truth is not available? Here, I'd like to add that replication example is just one scenario that we do not have the ground truth. The others include essay grading, peer review, and long-term geopolitical forecast. Let's come back to the main question. What does incentivize high-quality prediction mean here? It has two layers of meanings. First, we should incentivize truthful reporting. This is a basic requirement. Second, we want to make accurate forecasts get higher rewards. Suppose 0.8 is more accurate than 0.5, then the one who predicts 0.8 should get higher expected payment than the one who predicts 0.5. This probability encourages the participants to exert effort to get more information and to generate more accurate predictions. Our answer to this research question is a yes. We propose these surrogate scoring rules and a mechanism based on these scoring rules to achieve both properties simultaneously. Our challenge here is that we do not have the ground truth. So what we can rely on to incentivize the agents and to further measure the accuracy. Notice that the accuracy is a metric that is scored against the realized ground truth. There exists literature called peer prediction, focusing on achieving the first property, incentivizing the truthful reporting, where the second property has not been paid with too much attention. Here, we make a comparison to the latest work in peer prediction, EC20. They elicit categorical signals and achieve truthful reporting in a uniform dominant strategy, which we will talk about later. This is the strongest truth notion that has been achieved in this field, and they reward agents by certain mutual information between an agent's report and its peer's report. In contrast, we elicit probabilistic predictions. Mutual information is much harder to estimate for continuous variables or even for categorical signals with a number of classes. Thus, this mutual information cannot be applied directly to elicit probabilistic predictions. So we adopt a very different approach. We also achieve truthful reporting in uniform dominant strategy. Our reward recover the strictly proper scoring rules, as if you have the ground truth. We will introduce these strictly proper scoring rules right after. Here is the roadmap of our work. We will utilize the strictly proper scoring rules. They are the classic solutions that achieve the two aforementioned properties when the ground truth is available. Built upon it, we propose the surrogate scoring rules, which can achieve the two properties when we only have access to a noisy ground truth with known bias. Finally, built upon SSR, we propose the SSR mechanisms, which achieve the two properties even when neither ground truth nor noisy ground truth is available. Notice that the strictly proper scoring rules and the surrogate scoring rules can be applied to single question and single agent setting, while the SSR mechanism only works for multi-question and multi-agent setting. This is because without ground truth, we need to elicit the information of multiple tasks to verify with each other. Now, we first introduce the strictly proper scoring rules. Consider we elicit about how likely it will rain tomorrow. The ground truth will be resolved tomorrow with no cost, so the principal can pay forecasters by tomorrow. The principal pays the forecasters by a strictly proper scoring rule. The scores of prediction Qi from agent I against the ground truth Y, which will be resolved tomorrow. And it guarantees the truthfulness property that a function SQIY is a strictly proper scoring rule if and only if the following truthfulness inequality holds. That is, given any belief Pi of agent I, then from agent I's perspective, the expected reward is maximized when it reports Pi truthfully, other than reporting any other probability. So it maintains the truthfulness property by its definition. Here is an example. This is a quadratic proper scoring rules. It has this simple form. Now let's see how it achieves the second property. Accurate predictions get higher rewards. Suppose there is an unknown probability P star, which is a true distribution of Y. Then we can write out the true expected reward received by agent I. It is a constant purely determined by P star minus the quadratic distance of the true distribution P star and the reported distribution Qi. Therefore, if your report is more close to the true distribution P star, you will receive a higher expected score. This is the second property we pursue. This specific formula is just for quadratic scoring rules, but the similar property holds for all other strictly proper scoring rules, but just for a different divergence function. Now we have seen that when we know the ground truth, the strictly proper scoring rules can help us achieve the two desirable properties, and thus incentivize high-quality predictions. Next, we consider the setting where we have access to a noisy ground truth with known bias. We borrow the idea from machine learning with noisy label literature. Surrogate scoring rules extend the strictly proper scoring rules. They score a prediction Pi against a noisy ground truth Z with known error rate, which is defined by the first negative rate and the first positive rate. Surrogate scoring rules maintain the unbiasedness properties. The expected surrogate score R over noisy ground truth Z is equal to the expected strictly proper scoring rule S over the ground truth Y. This is how SSRs are defined. Here's one implementation of SSR. It is just a reweight of the strictly proper scoring rules using the error rates in its weights. We can see that if the error rates are both 0, then the surrogate scores degenerate to standard strictly proper scoring rules. We carefully design the weights such that the unbiasedness is guaranteed for any prediction and errors. Our research problem is solved when we have a noisy ground truth with non-error rates, because by this unbiasedness property of SSR, we can score a prediction as if we are using the strictly proper scoring rules and the ground truth. Now, the rest of the work is about how to construct such a noisy ground truth and estimate errors from only the agent's reports. This is what we did in the SSR mechanisms, when we neither have the ground truth nor a noisy one. We consider a multitask setting because if we only have one question, we cannot do too much with a ground truth. We consider a set of agent n indexed by I, a set of task m indexed by k. Each task is to answer a focused question, for example, how likely a study can replicate it. We denote yk the ground truth of task k, and pik the belief of agent I on task k, and qik the corresponding report. Each task is assigned to at least 3 agents, which also means that an agent does not need to answer all questions. We also need to make some assumptions about the information structure. First, we assume tasks are homogeneous and independent. Homogeneous roughly means that an agent has the same prediction ability on different tasks. Second, on each task, beliefs of different agents are independent, conditioned on the ground truth. Third, we assume that an agent adopts the same reporting strategy on different tasks. A pure reporting strategy is the mapping from a probability to another probability. Here, we allow mixed strategy. And this assumption means that an agent can use use the same mixed strategy across different tasks. In addition, we assume the principal knows whether there are more ground truths of 1 than of 0. This is just one bit of information. In the replication example, it is to know that there are more studies that can be replicated than the studies that cannot. Notice that A1 and A3 are common assumptions in multitask peer prediction literature. Now let's introduce the mechanism. When scores a prediction QIK for agent I on task K, let's recall the surrogate scoring rules RQIKZ. Our SSR mechanism has 3 steps. First, construct the noisy ground truth Z. Second, estimate the error rates. And third, apply the SSR. To construct a Z for agent I on the task K, we uniformly randomly pick agent J not equal to I and round Z being 1 with probability QJK. And QJK is the report of an agent J on task K. Then we need to estimate the error rate of this J. We notice that by this drawing method, the error rate of J on different tasks are the same for agent I. This is due to the fact that we assume that the tasks are homogeneous and agent adopts the uniform mixed strategy across different tasks. Then we use the methods of moment to estimate the error rates. The method is to establish statistical equations. On one hand, we can calculate a statistics on multitask data because the error rates are the same for different tasks. On the other hand, we can also express the statistics by the unknown parameters, which are the error rates. Then we can solve the equations out and find out the value for the parameters. This method has 2 advantages. First, it's distribution-free. Second, it is consistent estimates of the parameters. We establish 3 equations. Let P star be the percentage of tasks with ground truth being 1, which is unknown to the principal. The 3 statistics we choose are the frequency of a single drawn of Z on an event equal to 1, and the frequency that a double drawn of Z on an event both are equal to 1, and the frequency that a triple drawn of Z on an event are all equal to 1. The left hand of the equations can be calculated on data and the right hand are functions of P plus and the error rates. These equations have two symmetric solutions in closed form. Recall that we assume that the principal knows whether there is more yk equal to 1 than yk equal to 0, so they can identify the unique solution out of the two, and thus we complete the estimation of the error rates. Finally, we just need to apply our surrogate scoring rules against the noisy ground truth Z and the estimated ground error rates, because the expected reward is an unbiased estimate of the strictly proper scoring rules, as if we know the ground truth. Our SSR mechanism immediately inherits the two properties from strictly proper scoring rules. Incentivizing truthful reporting and accurate predictions get higher rewards. In this paper, we formally prove that truthful reporting is a uniform dominant strategy when we have a finite number of agents and tasks. When m and n is finite, this estimation error we introduce to the final reward is at order 1 over n plus 1 over squared n. When we allow the participants to specify at most 2 decimal digits, which is usually the practice, then we just need finite but sufficiently large m and n to keep the truthful reporting the uniform dominant strategy. To sum up, we achieved the two properties without using the ground truth. We tested our SS score on 14 datasets from 3 real-world human forecasting projects. We found that the SSR is very close to the true score. Its regression coefficient towards the true score is close to 1, and the interception is close to 0. And we compared to other peer prediction mechanisms. SSR mechanism demonstrates the strongest correlation to true score. Finally, let's go back to our example of predicting the replicability of social studies. Our SS score mechanisms have been adopted into the system as the incentive scheme for the forecast surveys. For people who are interested in it, you can access the blog of the replication markets, which is a project under this big grand score program. There is a discussion about the robustness analysis of our SSR scores. Now we can wrap up our study, and here is the acknowledgements.